morning there in Norway as
Early
well.
morning for me, but late for you or later for you. Give me just one more second to make sure. What's the weather like at the moment, if I may ask?
Yeah, weather is quite pleasant
I was feeling.
because spring is in the air at the moment in Lahore. So it's shifting. Light shower yesterday, rain,
Mhm.
and now the weather is full. The sun is in full moon at full bloom at the moment, and
That sounds
with
lovely.
with a little cool
Oh,
wind, breeze wind.
and now I see that Carlos
Yeah,
is at.
Carlos
Oh,
and Beatriz,
now I see. I
they are in
see.
the
Okay,
second
now I
venue
understand.
now in
I
Karachi.
understand. I understand. Yes. Okay. Very good. So I hope I can imagine that you're very exhausted already at the end of a second week. So for me, it's just 1 week so far, and I'm also feeling the excitement that comes through this channel. So I can only imagine that it must be even more thrilling being there live. So today I want to talk. So the first two lectures we have seen, as I said, a huge toolbox of results that span from real algebraic geometry, from linear algebra, namely representation theory, to algebra and algebraic geometry, which we saw invariant theory. And now I want to span this arrow even longer and go to real algebraic geometry and optimization problems. And I want to, again, a little bit more practical today, tell you a little bit about things that I'm very interested in, namely how we can use symmetries to actually reduce and simplify problems. Namely, I mean, one example of that we will be looking today, polynomial optimization problems, okay? So, and the goal will be to see that how we can actually simplify those problems that I will just mention, introduce in 2 slides, with tools from representation theory and invariant theory to simplify things that maybe otherwise would not be calculable. And then I also want to shortly just motivate another approach that's maybe at the end that works for symmetric polynomials. And again, throughout this lecture, G will be always a finite group which acts on Rn now. So this is the main difference to the first two lectures. We are now working in a real setup. And I just mentioned this always a little bit briefly. All the results that we had on representation theory and invariant theory, I stated them over C. So there is actually, I'm maybe also now putting some things under the rock by the small difference between R and C that is actually very important to keep in mind. And this, in practice, this sometimes needs to be taken care of. And we had already seen how we can use Schur's lemma to simplify matrix calculations. Now we want to see how we can actually use this to simplify those optimization problems. So this now just concretely means, again, almost the same setup that we had before. We have a group and it acts now linearly on a real vector space. So we have a real representation that's just now a morphism to the general linear group over the reals. It acts then in the same way on the polynomial ring as we had it over for the complex setup. And again, I say a polynomial is invariant if the group action does not change anything in the polynomial. And again, I write the polynomial ring upper G for the invariant polynomials. And again, this is a subalgebra, is a subring. And we had already seen there was this important operator, the Reynolds operator, and of course, this is exactly defined in the same way. So this is just a repetition. All these things we have seen in the second lecture, actually. Okay, so this was nothing new. Let's start with the actual new thing. So we want to talk about symmetric polynomial optimization problem. So POP stands for polynomial optimization problem. And by this, I will mean the following. So again, we have a bunch of polynomials, F, G1 up to K, real polynomials. And they define the polynomials G define a so-called semi-algebraic or basic semi-algebraic set, by which I mean it's just the points in real space such that all the polynomials G are non-negative. Okay, so this is some region in n-dimensional real space that is described by polynomial inequalities. So I have already used the polynomials G1 to Gk, so there is the polynomial f is still left. And a polynomial optimization problem is then the question, find the minimum value or the infimum value, actually, maybe we don't know if it's attained, the infimum value of this function, this polynomial as a function on the set K. So what is the smallest value that that f can take on K? So just as a motivation, I mean, a lot of problems in spanning from combinatorics to real life applications can actually translate it in such a setup. So this is a very rich setup, which also means in general it's a very hard problem to solve. In the setup now that K, our set K, is not just any semi-algebraic set, but it's closed by the action of my group G, which I just mean whenever I have a point in K, its entire orbit is also lying in K. And I further assume that f is a G invariant function, so that also the values that f takes on K don't depend, only depend on the orbit. Then I will just say it's an invariant, a G invariant polynomial optimization problem. Okay. So this is what we will be studying today. I mean, one obvious drawback of being invariant is, of course, I mean, if I have computed one solution, normally if I have a normal action of my group on the set K, whenever Carlos found me one, so I'm using Carlos now as a person in the audience because he's the only one that I can see clearly. Sorry for that. If he has computed one solution for me, I implicitly know already that there are many more solutions, most likely, namely for every solution, I will have the entire orbit. So if you just naively start to compute, I mean, you might just run into the problem that you might compute a lot of points, but the actual information gain is not really big. So whenever I have, let's say, a local minimum, I get all the other local minima where I just actually don't get any new information with respect to the value that I'm interested, because the value of my function is the same on all of these. So this maybe suggests already that it would be very good for us if we can reduce the symmetry that is in this problem. And this is exactly what we want to do today. And we will not, I mean, I will not talk about general polynomial optimization problems. I will already look at something that is a new or has been in the focus of interest in last years, that connects. I mean, this is maybe something where you think this is more something analytic. I will actually look on the algebraic side. I will focus on so-called sums of squares relaxations of polynomial optimization problems. So to actually tell you a little bit what this is, let me start a little bit. So suppose, and I will only care about for the lecture, I will only care now for the simple case when K is just the entire space, to make things a little bit easier. But everything can be, of course, generalized to this setup. So suppose I have a real function, a real polynomial function P in n variables, and I want to find the minimum value. This is, of course, a very hard problem. I mean, so we do this in calculus, or actually in high school for one variable, you do this in calculus. The normal way of doing this would be to compute critical points, right? I mean, you compute all the critical points, and then you check which of the critical points maybe is a global minima. And then, I mean, at the end, you maybe have to look around what happens on the boundary. And in calculus 1, 2, 3, 4, I don't know when, you learn how to do this in higher dimensions with Lagrange multipliers. So there is an algebraic way of doing this. There is an algebraic system, of course, you can try to solve, and you get all the critical points. But critical points might just completely blow up the number of critical points. So there's another idea is just to rewrite this problem. So the goal here, maybe the motivation is, I'm not interested in finding the points that minimize this function. I'm just interested in the value, the minimal value, or the infimum value. So I could actually also reformulate the problem. I just could say, well, the minimal value that my polynomial takes is the same thing as the supremum over all lambda, which I can subtract from my polynomial, guaranteeing that it stays non-negative. So this is a little bit maybe twisting the head around. So the minimum value of the polynomial, I mean, if you think about a parabola, a parabola in one variable, I mean, the minimum value being down here, and then the difference between, let's assume it's positive, then the difference between the minimum and the x-axis, that's exactly how far I can move my polynomial down such that it hits the x-axis. So the minimum is exactly the same as the maximal number that I can subtract from my polynomial to ensure that it stays non-negative. Okay, so I have now reformulated this problem. And the interesting thing is, if ever somebody gives me a lambda for which this condition holds, namely that p of x minus lambda is certifiable non-negative for all x, we don't necessarily have the minimal value, but we have a bound for the minimum value. So this is actually giving us a little bit more information. And
Excuse
me.
Yes.
Cordian,
Yes.
you are searching for a global P star, number one, and number two, what ensures about the existence of this P star?
Oh, I mean, so it's just, I mean, okay, in the general setup, of course, this is just the infimum now. So I mean, we have to be a little bit careful because I said I'm a little bit quick here, but yes, you're right. I mean, in general, maybe we have to only look over a compact set, and then we can be sure that this exists.
Okay, only on the compact set. Okay,
so the x exists, then we have the infimum, but the infimum exists, right? I mean, the minimum value exists always. The infimum value.
Okay.
The
So
value,
you are
value. I'm just looking for the value. That's why I said I'm looking for the value and not for the points.
okay.
But the important thing is whenever I have a lambda that satisfies these inequalities for all x. So this is an inequality p of x minus lambda that needs to hold for all x. If for some reason I have such a lambda, I have already a bound for my infimum value. So just having this lambda gives me, even if I maybe have not found the best lambda, just having one lambda is actually very good. But I mean, again, the property that I have here is very simply stated. But I mean, again, how do I check if this actually, how do I check if this holds? So the problem is, of course, that checking if a polynomial is non-negative is a very hard task, and it's exactly as hard as the previous one. I mean, we have not gained anything here. But it opens the door for something that connects now a little bit more to algebra. Again, I mean, so I call a polynomial positive semi-definite. I mean, if it's homogeneous, maybe for forms, or non-negative, if and only if it attains only non-negative values. Okay, so if whenever I put in A, I have a non-negative number. Okay, obvious. But that's nothing new. But now I say that a polynomial is called a sum of squares, SOS. Okay, again, also the name already hints to what it is, if it can be written as a sum of squares of polynomials. Okay, so if my polynomial P can be written as q1 squared plus 2q squared plus qm squared for some polynomials q1 to qm, I say my polynomial is a sum of squares. Okay, why is this interesting to have a sum of squares? So first of all, this is obviously an algebraic property. So I mean, if somebody comes to me and hands me the right-hand side of this equation, namely this q1 squared plus 2q squared and so on, I just have to check algebraically, linear algebraically, that the two sides agree that P is actually this decomposition. This is just comparing coefficients, and obvious by the right-hand side, obvious if somebody gives me a sum of squares, obviously I know that it's non-negative, right? I mean, this is just, I mean, we all know that squaring makes things positive over the real numbers. So if I have a sum of squares, there is no way that this is not non-negative. So such a decomposition gives an easy certificate that actually something is non-negative if I have it. And it actually gives me thus this bound lambda that I want to have. So one example, I mean, if I give you this polynomial, Carlos, this polynomial has 3 variables and it's of degree 8, sorry. It's hard to count sometimes. If I would give you this polynomial or anybody else in the room, and I would ask you, is this non-negative? Well, you would think maybe, maybe not. I mean, has some even terms, so it's maybe more even than not even. So maybe it's non-negative, maybe it's not. I mean, this could be also a trick question. But if I just give you this expression here, which is the same, I mean, in this you can now check by just expanding it. I mean, if I give you this expression and I ask you the same question, is this non-negative? I hope that everybody in the room will only use 10 seconds at most to think about it and will agree, yes, of course, this is non-negative. So this is the difference between the question non-negativity and having something as a sum of squares. So it is sort of an algebraic question. I mean, it is an algebraic question, and an answer to this algebraic question gives us a lot of information on the actual function. So this is very exciting actually to have. And I mean, we won't go into details here. The good thing is there are very good algorithms to compute such a sum of squares decomposition for a given polynomial. So whenever I have a polynomial, I could ask myself, well, I mean, is there these Q1s to Qms that actually have this property? And it turns out, yes, there is an algorithm to do that. And this algorithm is, I mean, there's an algorithm for everything almost. But I mean, it's an algorithm that I actually can use that works pretty well. I mean, in a lot of instances, and that's maybe much better than just calculate all the local minima.
Excuse me, Professor, I have a question.
Yes.
What can we say about the denseness of the sum of squares?
Very good question. I was just about to tell you. I mean, I was just about to see. I mean, maybe you should ask more questions. Then I can immediately answer them. So, of course, in a perfect world or in a world where hard problems are easy, sums of squares, every non-negative polynomial would be a sum of squares, right?
Yeah.
Perfect.
Yeah.
But turns out the world is not perfect if you have not found out so far. There is flaws in the world, and this flaw was already found by Hilbert again over 130 years ago. He was able to show that, I mean, in general, most often sums of squares are much smaller. I mean, the set of sums of squares is much smaller than the set of non-negative polynomials. So only in a few cases that he classified, namely quadratic forms, univariate polynomials, and these ternary quartics, we actually have that sums of squares are the same as non-negative polynomials. So that's, of course, a bad question or a bad situation. So you might still think, okay, why do I care? There are other results that, I mean, tell us, and this answers your question, that tell us that depending a little bit how we interpret this question of denseness, if we only look at polynomials of a fixed degree, if we look at polynomials of all degrees, there is actually situations where sums of squares, I mean, where a lot of non-negative polynomials are sums of squares. So there is some interesting results from Blackerman, for example, a negative result that showed if I fix the degree and I let the number of variables just grow, then most likely, I mean, the set of sum of squares becomes very, very thin compared to all the polynomials of this given degree. So that's a negative result, and kind of a different result if I think about a polynomial as a long string of coefficients, and I don't look at the same polynomial only in the same degree, but I allow myself also for perturbations of higher degree terms. So then actually sums of squares, every polynomial that is non-negative can be sort of approximated by sums of squares if I go up with a degree. So
okay, thank you very much.
This is quite an interesting question that you had, and it would be worth at least 4 or 5 lectures of its own right, just to talk about this approach. Okay.
Thank you very much.
You're absolutely welcome. And of course, I mean, so one can restrict the degree, but I mean, one also could say, well, I also want to maybe look not only on all polynomials, but maybe also on polynomials where where I have some certain other properties. They could be very sparse, for example, or I mean, I could look at polynomials that are invariant by some group. And this has been already done in the 80s and 90s by Joy, Lam, and Resnick, and the student of Bruce Resnick's called Harris. And very recently, this has gained a little bit of attraction again by various other authors, so including myself. Okay, so this was just the first. This was a motivational starter, maybe. So just remember, the important thing is now we're looking for sums of squares of polynomials. Okay, so I have a polynomial, and now I also have this polynomial is invariant by a group. And I suppose now I know that it's a sum of squares. I know that P is a sum of squares. So so I can write as a sum of squares. So the question is a little bit, how can we use our whole setup on invariant theory? So remember, we had this whole beautiful theory that there was the subring of invariant polynomials, and we can really nicely calculate with these invariant polynomials maybe. How can we make use of this? And the first unfortunate news is that, I mean, maybe obviously, but I mean, just to highlight this, only because P is invariant, we don't know that the QIs are invariant. Moreover, I mean, in general, there is no reason to assume that we can find such invariant polynomials QI. One easy example, I look at this polynomial x1 squared plus x2 squared and so on to xn squared. This is a symmetric polynomial. It is obviously a sum of squares. I mean, all the summands now are squares. I mean, all the summands are not squares, of course, are not symmetric, but you might still wonder if there is maybe a symmetric polynomial that when I square it gives my polynomial p1 squared to p2 squared, x1 squared, x2 squared, and so on. But if you think about, there is only one polynomial of degree 1 that is symmetric, that if I square it would come up to this polynomial, and the only one polynomial that is symmetric is this polynomial x1 plus x2 and so on. So there is no way, if n is bigger than 1, that we can make this polynomial square it somehow to come up with this polynomial on the right side. Very easy example. So in general, a polynomial that is invariant needs not to have a sum of squares decomposition in terms of invariant squares. Okay, so that's already maybe a kind of a disappointment here. But we also had these tools from representations theory that I mentioned in the first lecture. And the goal today is now to see how a combination of these two tools can actually help us to get hold of this question, how we get actually symmetry reduction for this question of sums of squares. Okay, and the goal, what I thought is how I do this is, I will only first look at this very kindergarten example, let's say. It's a very simple example. I will just use the simple group S2 that acts on a two-dimensional vector space or on a polynomial ring in two variables by interchanging x and y. Okay, this is a very simple example. And I will use the following two facts that I have already mentioned to you. And I had already mentioned their generalizations. So the goal is a little bit to see in the simple case first what's going on, see how it generalizes, and then get the whole theory. Okay, we had already seen as an example that if I have an invariant polynomial, a symmetric polynomial in the two variables x and y, I just now use x and y to emphasize that we have two variables, then we can uniquely write it as a polynomial f twiddle in p1 and p2, where p1 and p2 are just these power sums. So it's x1 plus x2 and x squared plus y squared and x plus y. Okay, so these two polynomials. So I find a new polynomial twiddle that is uniquely determined. That's, I mean, it's a little bit important, but not the main point. In two variables, z1 and z2, such that whenever I plug in p1 and p2, I get my original polynomial f back. Okay, that was the invariant theory part. And the other thing that I also briefly mentioned is that in fact every polynomial in two variables, not necessarily a symmetric polynomial, can be written in a unique way as p1 plus P2 times x minus y, where P1 and P2 are symmetric polynomials. Okay, so these two facts we have seen in the last lecture. They are actually incarnations of representation theory and invariant theory, but for this simple case, they are actually very simple to prove, also elementary. So up to this point, we would not need all this heavy machinery. Okay, let's just now use a little bit, and I will later tell you, of course, how this generalizes, but let's just see a little bit how we can make use of these two simple facts. So again, let's start with the polynomial f. I see I always switch between f, p, and q. I'm a little bit inconsistent here, sorry for that. So I start with this polynomial f, which is a sum of squares, and I assume that this f is invariant with respect to this switching of x and y. Of course, and we have already seen, this invariance of f does a priori imply nothing on invariance of f in different fi's. Okay, but I want to see now how I can exploit this simple symmetry. So by effect number B, we can start by saying, okay, well, fi is not invariant, but every fi can be in fact written as fi1 plus fi2 times x minus y for some symmetric polynomial. So it's not a symmetric polynomial necessarily, but it has these two symmetric polynomials attached to it in a way that it can be uniquely written as this linear combination that you see here. Okay. And then if I square it, if I square it, I see immediately, okay, if I square fi, I get a square on the left side, I get a square on the right side. And now you see if I square x minus y squared, if I square this, I get an invariant polynomial. So now this change of x and y doesn't change anything on x minus y squared anymore. So I have the left-hand side is invariant and the right-hand side is invariant. And in the middle, I have a term, two invariant polynomials times x minus y. Okay, that's also just simple algebra. So if I do this for all of them, I immediately get this decomposition where I have the left-hand side invariant polynomial squared, right-hand side invariant polynomial squared, and in the middle, I have something that is not invariant. Okay. So now, of course, I want to use that. So this, of course, also would have worked for any other polynomial. So far, we have not used that f itself is invariant. And but if I now interchange f, x and y, so if I switch f and y, you see what happens to the middle terms is that I switch x with y in this factor in the front, I get the negative of that term back. Yeah? So if I add f of x and y with f of y and x, these middle terms will just cancel out. So by doing this simple trick, f of x and y is the same as f of y and x. And so I just should take the half of them, of the sum. I actually cancel out all the middle terms. And I have now a really neat decomposition of my polynomial in terms of polynomials that are squared, that are invariant. So let me just see now. I have invariant polynomials standing here, and I can now rewrite these polynomials in this P1 and P2. So what we have is, and this is now, if I look at my polynomial f, and we have already seen that I have this unique determined polynomial f twiddle. So now I want to use all of this to say something about my f twiddle. Namely, I know that my f twiddle will be of the following form. It will be a sigma 0. Sigma 0 is an invariant polynomial, and is actually a sum of squares of invariant polynomials, and a sigma 2, which is again a sum of invariant polynomial squares, times this term that you see here, this 2 pi 2 minus pi 1 squared. This 2 pi 2 minus 2 pi 1 squared. This is just the thing that we get by doing this calculation. This is exactly just this x minus y squared expanded in invariant polynomials. Okay, so we get a certificate. So the important thing is with this theorem is if I have a polynomial f, I can compute the polynomial f twiddle. And by seeing this decomposition that I can and also algebraically check, I now know that my original polynomial is the sum of squares. Let me say this again. F twiddle is not a sum of squares of polynomials in the ring of R of pi 1 and pi 2. However, I know that this representation guarantees me that my original polynomial was the sum of squares. Okay. So actually, I mean, this is maybe a fun exercise to do. So one could just try to see a little bit how the number of coefficients that I have to use to check if a polynomial is a sum of squares. In the two representations, f in x and y and f twiddle in pi 1 and pi 2. Actually, I mean, just playing a little bit around with the degrees and the coefficients involved in these two expressions to see that actually checking that this second condition holds is a little bit easier than checking that the first condition holds. I mean, it's just a little bit easier because also, I mean, the group that we had was not actually so exciting. Okay, so now let's try to generalize this a little bit for the permutation action of Sn on Rn. So we know, and this we have already seen, that in general, for not only for the simple toy play game of S2, but for all Snx permutation actions on Rn, we have that the ring of invariance is generated by n algebraically independent homogeneous polynomials Pj, which are exactly these power sums. And another thing that we have already mentioned earlier is that, I mean, we have a similar property to the property B of previous, namely we have that the polynomial ring was a free module over this ring generated by the homogeneous fundamental invariance pi 1 to pi n. Okay, this we have seen in the second lecture. So A is the direct similar consequence to F to the condition A previously, and B is, I mean, morally exactly the same statement. Okay, so again, the above theorem tells us that every symmetric polynomials in the x1 to xn can be uniquely written as a new polynomial f twiddle in those variables pi 1 to pi n. And fact B is just telling us, again, we have for every polynomial, we have a unique representation. I mean, we can find a family of polynomials, b1 to bn factorial. So we have, I had already mentioned also that the rank of this module is n factorial, is the size of the group. So in our case, n factorial. We can find a family of polynomials, b1 to bn factorial, such that every polynomial, not necessarily symmetric, can be uniquely written in this form. Okay? Very good. So how can we now make use of this factor b prime in a convenient way? So again, we do exactly the same thing a little bit. So we see, okay, again, if I have my p that is written in this unique way with the help of this basis, then I square it. I mean, this is just also a very simple thing to do. And now I just want to use a little bit abusive notation. I take two matrices B and P, which are matrices of size n factorial times n factorial. So this is maybe already too much for most of our piece of paper to write down when n is big. I think of P, the matrix P, as just these terms P1 to Pn factorial transposed P1 to Pn. So this is a huge square matrix where I have the pairwise products of these Pi's inside. And I do the same thing with the matrix B, where I put the pairwise products of these B1 to Bn factorial in. And with this at hand, I can just simply write P squared as shown here as the trace of the product of these two matrices. Okay, this. So and sorry,
what is A? Sorry, what is A?
What is A? Very good. A should be P. A should be P. Very good. Very good point. Very good point. Very good point. See, this is Yeah, this is again one of these exercises I hide mistakes so that somebody can tell me that they're still awake. Very good. More generally, of course, now if I have a sum of squares, I mean, and this is where it's getting maybe a little bit more interesting why I did this. So I can do this, of course, for every of the PIs, but since trace linearity, I can actually write my F in this form where I take the sum of these matrices as a first matrix and then times B. And the PIs are defined accordingly, okay? So the intermediate result that we get by this is just, okay, if I have a sum of squares polynomial, then I can find matrix polynomials, A, which is the sum of these P1s to Pk, which I have to find. I have selected the spaces. The spaces I select beforehand. So for every polynomial, I can, of course, use the same basis B. I have already this matrix B at hand. So I want to find these polynomial matrices P1 to Pk, which have to be square matrices. So they have to be squares of these polynomials for some symmetric polynomial, okay? Such that my polynomial F can be written as trace of, again, I did A times B. So this is where the A comes from. So the A is the sum of these P's. Now I get where I got this A previously, okay? And again, we have this very nice operator that you have already seen. I just call it now sym_n, which is the Reynolds operator. I just call it sym because I want to stress that we are doing this symmetrization with a symmetric group. This, of course, lets my polynomial F invariant, so I can start with F, I can symmetrize it, I symmetrize it, and I essentially take, by linearity, I take the symmetrization into the product, the trace. The matrix A is already a sum of squares of invariants, so it's all of the entries are invariant, and I only need to symmetrize the last matrix B. So I know that there is another symmetry. I mean, so I do this component-wise. So I know from this result, just by linear algebra, that there is another matrix B that now, I mean, with the symmetrization of B, which is containing only invariant or symmetric polynomials. So again, I can find a matrix B twiddle that I can write in the polynomials P1 to Pn. Okay, so the whole game was now just I reduced. So before I had where was it? I mean, before I had n variables x1 to xn. Now I have again n variables, but now they're called P1 to Pn. Okay. Okay, so this was already helping us a little bit. So I mean, now I reduced the whole thing from the polynomial ring, from a question in the polynomial ring to a question in the invariant ring. So now, I mean, this is the interesting thing. Now all the polynomials involved are invariant, and I can do calculations in the invariant ring. So now I want to bring a little bit of representation theory into the play. So again, I have this action on my Rn, which gives me this action on my polynomial ring. And we have a G module structure. So of course, there's a little bit of warning here. We only did this for finite dimensional vector spaces, but I mean, we can grade the polynomial ring, and the group action respects this grading. So actually, we can work ourselves up in this grading. So we can actually each of the individual pieces decompose this nicely. So in the end, we get a decomposition of my polynomial ring in terms of this isotypic invariance that we also had mentioned in the second lecture a little bit. Okay, so important thing is I can write the polynomial ring as a direct sum of these isotypic components, and we have already seen also that these isotypic components themselves are free modules over the invariant ring. Okay, so now the following is actually a direct consequence of Schur's lemma. So the following is, whenever I take two polynomials f1 and f2 that come from two distinct isotypic components, okay, when I take two polynomials, so I have this decomposition, I take one polynomial that is in one isotypic component, I take another one that is in another isotypic component, I take their product and I symmetrize it, I get 0. Okay, so this is the generalization of the simple fact that whenever I take whenever I take this product with this polynomial x minus y, and I symmetrize, this got cancelled, and now I just generalize this with Schur's lemma to all kind of distinct isotypic components. And this is not hard to see. This is really just, you have to cook up from this product a good G homomorphism where you then can apply Schur's lemma on. Okay, so remember Schur's lemma told us that if I have two distinct irreducible components in a vector space, then there is no non-trivial G invariant homomorphism between the two of them. So what you do here is you just build a homomorphism, and then that is G invariant from this product, and this has to be 0 in the end. Okay, it's a little bit not so interesting. So, but again, if you're interested in that, a good exercise might to be really try to figure this out with the help of Schur's lemma for general finite groups. So because again, I mean, everything I'm telling now actually works also for finite groups and even more general. So we saw that we can actually, as these consequences of Schur's lemma, we saw that we can actually find a nice symmetry adapted basis for representations. So I can actually find a nice symmetry adapted basis also for my polynomial ring module basis in this P1 twiddle to Pn factorial twiddle, which allows us to get a block diagonalization of the matrix polynomial above. So that's a lot of things coming now together. So the important thing is I find a new matrix which is exactly the same matrix as it's the pairwise product, but now it's the pairwise products of this B twiddle, and I symmetrize it. And Schur's lemma will guarantee me that the matrix that I get will be of block diagonal structure, so it will sum directly as these smaller matrices B twiddle Hi, where each of these corresponds to different isotypic components. We had already seen yesterday that I can actually compute the sizes of these blocks and so on with characters, so that this can be done all very explicitly. All the information you can read out ahead of time. Okay, so and with all of this magical tools, what we have actually shown now is that whenever I have a sum of squares that is symmetric, and I take the uniquely corresponding polynomial f twiddle in my invariant ring, then I can actually find in the invariant ring a representation of f twiddle in this form. I mean, this looks like a little bit maybe horrible because suddenly there is matrices involved, but once you take the trace and so on, it's actually just a polynomial identity again, right? I mean, this is just a very convenient way of writing this construction. So this is why I kept it. But in the end, it's just a condition on symmetric polynomials that you explicitly can write down in the same way as we have written down this first conditions for the two variables case. Okay. So the important thing is, so the specific decomposition might be much more simple, because I mean, if we have some, I mean, for general f, maybe it's not so clear what this means, but I mean, the polynomial f and f twiddle, they might be very different. I mean, f twiddle may have much lesser terms, for example, if I make a nice choice. So the computations may be much easier in the invariant ring than in the original ring. So let me just give one concrete example. So in the quartic case, so if I have a polynomial of general number of variables that is of degree 4, and I want to write as a sum of squares, so we know it is a sum of squares of quadratic forms. I mean, it's quartic, so it's of degree 4. All these things that I square have to be of degree 2, otherwise I don't arrive at quartic polynomials, quartic homogeneous polynomials. So you do all these calculations, you end up actually with two matrices, B1 and B2, which you symmetrize in this. I mean, how I got up to this polynomials is maybe still a little bit mysterious, but I mean, again, this is just representation theory used. I mean, you can use these projections that we had. So you get two matrix polynomials that you can symmetrize, and every homogeneous polynomial of degree 4 in whatever number of variables can be uniquely written in the invariant ring in this nice way. So I mean, you have one invariant symmetric polynomial, one invariant symmetric squares polynomial. You have this inner part here, which is this matrix B1 here coming into play, and the matrix B2 is just the polynomial itself, right? So it's a very simple representation, and now this gives us a representation in the invariant ring instead of in the number of variables n before. So actually, the interesting thing is that the sizes of these matrix polynomials that I gave in this theorem, remember, I mean, this is a 2 by 2 matrix and this is a 1 by 1 matrix. And what I'm claiming here, and I didn't mention this maybe good enough, is that the sizes of these polynomial matrices does not depend on n. Right? I mean, this is just, and they actually can be efficiently calculated because, I mean, if you look at this symmetrization operator here, I mean, there's not much going on. It's just x. It's two variables. It's two variables all of the time. It's 4 variables here. So I mean, it's actually very easy to calculate the symmetrizations of these products ahead. I mean, like parametrically with n. So this is very easy calculatable. And actually, what one gets in this way, and I mean, a little bit cheating here, that actually, if I have a quartic polynomial in whatever number of variables, it's easy. It's the question of checking if this polynomial is a sum of squares does suddenly no longer depend on n. So it's as hard or as easy to check if a symmetric sum of squares of degree 4 in 100 variables is a sum of squares than is for 1,000,000 variables. A little bit, I mean, maybe numerically unstable because these coefficients, I mean, there's this coefficient n is somehow inside. So this is a little bit, of course, something we have to keep in mind. And this is actually something that is more generally true and which makes the symmetric group case very interesting, namely that checking if a symmetric polynomial of degree 2D in n bigger than 2D many variables is actually independent of n. So this just comes from studying this isotypic decompositions of the invariant ring. Okay, again, so the proof of this theorem is just finding a unique representation of the PIs. That's, I mean, the degree of my polynomial already tells me that because these PIs, they have PIs, they have a certain degree. And as soon as their degree is bigger than the degree of my original polynomial, they will no longer appear in my polynomial. And also one can find a nice basis, module basis for the polynomial ring with this property and the unicity. So these are called higher spec polynomials, which are also actually very interesting to study from a purely algebraic point of view. They give very nice ideals. And so in that way, one gets immediately that all of these things, all of the data, if you fix the degree, all of this data stabilizes very quickly.
So Cordian,
Okay.
could you explain a bit more? So what's the algorithm in this complexity statement that you're talking about? So you're giving a polynomial.
Yeah. So again, this was a little bit. I wanted to make it vague, and now Carlos is actually. So I mean, what I should have said is, so the polynomial expression that I get, that I need to check if it's a sum of squares. I mean, okay. So I mean, this now a little bit for the expert. So to check if a polynomial is a sum of squares, I mean, you have to build up matrices, right? So-called Grime matrices. And you have to solve a semi-definite feasibility problem. You have to show a polynomial is a sum of squares if you can find such a Grime matrix for my polynomial that is positive semi-definite. So what I actually should have said is that the size of these Grime matrices and the n does not grow, so that does not grow with n. So the sizes of these matrices does not grow, and the entries of this Grime matrix that I need to check can be explicitly written down parametrically. So the cruise is that they actually are parametrically dependent on n. So they are not the same. It's not the same problem that I need to solve for all n, but it's almost the same problem. So there is this small parameter n in here, and that's actually why the statement is very, very maybe misleading, because of course this might tend, for n bigger and bigger, this might tend to 0, and then you run into numerical instabilities and so on. So this is why I should have been a little bit more careful here. But the important thing is the data for the algorithm, I mean, doesn't depend on n. I mean, it depends on n, but the sizes don't depend on n.
Yeah, thank you. That helps. And so one more thing. So then, do you have an expression for this size? Is this polynomial?
You can. I mean, the size is. I mean, the sizes, they are all expressible with this representation theory. I mean, for the symmetric group, you can actually use a little bit more combinatorics. So the symmetric group has a very nicely understood representation theory that ties beautifully to combinatorics, beautifully to a lot of other things. Maybe I will have a time a little bit in tomorrow's tutorial to talk a little bit more about this. But actually, so there is a very nice theory that gives you all of this information. I mean, not for free, but in the sort of, you can look it up in a book. Yeah, it's all
Kind of like hook length formula or something like this.
Hook-like formula, exactly.
Thank you.
Okay, so of course, all of these results generalize to finite and even more reductive groups. So you have a polynomial, we have already seen. It can be, the polynomial ring is the invariant ring is generated by not necessarily algebraically independent, but still by a finite number of homogeneous polynomials. And also we have seen that the polynomial ring is a module over the invariant ring, but now this is no longer a free module. So there's some problems here that make the whole thing less nice and a little bit more tricky to work, because you no longer have freeness in all of these representations. But I mean, the freeness actually was never really important. It's just convenient, and it just helped us, for example, to reduce the degree, and so obviously. But I mean, the freeness was not really important. So all of these things can be generalized directly. So the theorem that I gave you for the symmetric group, for the symmetric sum of squares, actually literally generalizes to all other groups, with the only thing that you have to remove whenever I wrote uniquely or so. And we can analogously define also these matrices by B for all the irreducible characters. And I can calculate all of these things. Again, it's maybe a little bit more challenging to do the actual calculations, but I can do all of this modulo the things that I have, the syzygies amongst them. So the take-home message is that whenever you have a sum of squares that is invariant with respect to some, when you have a polynomial that is invariant with respect to some finite or maybe even reductive group, you can use a combination of representation theory and invariant theory to actually compute the sum of squares relaxation. And this can actually drastically simplify, in terms of invariant theory, my original problem. Okay, so of course, I mean, one should keep in mind that this is, of course, all very nice, but I mean, all that we did is we just simplified calculations, right? I mean, so I reduced some calculations by making sure that I mean, I don't compute too many things that I actually implicitly have already computed. So reducing symmetries just remove things that are in the same orbit, if you want to say. However, they did not fundamentally change anything in this problem, in the sense that one person correctly asked, I mean, how do we actually, I mean, if my polynomial is not a sum of squares, it will not be a sum of squares magically after any of these magic that I did here, right? I mean, either it is a sum of squares or it's not a sum of squares. And I mean, I just reduced the complexity of checking if a polynomial is a sum of squares. So I want to spend the last 5 minutes just by emphasizing something completely different. Suppose I have a polynomial optimization problem again, and suppose that somebody, let's say again Carlos, because he's a magician and a Jedi master, knows a priori that the symmetry of the solution. He tells me, okay, don't worry, I can assure you that the solution is a fully symmetric point, if you want to think about the symmetric group. So I can assure you that you only have to check points that have full symmetry. Well, this, of course, drastically simplifies the problem because we only look, in this case, on a one-dimensional line, right? I mean, all points with the same coordinates. So this would be really good news if Carlos would have such an information. And I mean, one example where this is happening is if I have a convex optimization problem. So if the objective function is convex, and the feasible region is convex, then actually by just averaging in the same way that we did with this Reynolds operator, we know that there will be always an invariant solution. So this will actually drastically simplify. However, I mean, convex optimization problems normally are themselves already easier. So, I mean, maybe they are not the interesting things to look at. So I just want to briefly mention the following thing. So, I mean, suppose we look now at Rn and we classify points that have at most k distinct components. So coordinates, a full symmetric point, all the coordinates are equal. If I just now restrict at points that have not all coordinates equal, but at most k of them are distinct. So in other words said, these are points that are not stabilized by the full symmetric group, but they are still stabilized by a big subgroup of my symmetric group. Okay, so there's a very nice theorem that I'm a little bit proud to mention. And this actually tells us, okay, if I have an optimization problem and all the polynomials that are involved are symmetric, so this now specifically only works for the symmetric group, and all of them are symmetric, and the degree of them is fine. I mean, it's bounded. It's always bounded, but is nicely bounded so that that it's small. The degree is, so I can define this number k to be the maximum of 2, half of the degree of my p, and the degrees of these g1 to gm. Then actually I know that the minimum value of the polynomial will be attained of points with at most k distinct components. So this gives another nice way of actually doing this. Well, I mean, how do we do this? I mean, this is maybe a little bit running out of time now, but again, the thing is just, well, I mean, now you look at all the possibilities of building points with k distinct coordinates, and then you basically branch your problem in different subproblems, namely you check for all of these various choices of problems. I mean, you essentially get a new, instead of one problem in n variables, you get some number of problems in k variables, and the minimum of your original problem is the minimum over all of them. So you can then actually also apply all of the techniques to the individual problems. They have less symmetry, so the symmetry is already taken care of implicitly because we have assumed that the points have some symmetry, and you thus reduce not only the computation, but you actually reduce the dimension of the problem drastically. And this then also has interesting things where, I mean, you've seen this Hilbert, for example, showed that univariate polynomials are always sums of squares. So if you start with a symmetric polynomial and you know that you can only restrict on the one-dimensional part, you can immediately go to one dimension, and then you know that you can actually use sums of squares relaxation that will be exactly giving the solutions. Okay, and there's other examples where you can do that. Okay, that was just maybe a side track to show you that there's also other techniques in the setup that can be used. There are some generalization of these results to other, I mean, I mentioned already finite reflection groups, but it seems to heavily depend on the actual situations. So the take-home message number 2 that I just wanted to tell you is, if you are ever in the situation that you have polynomial optimization problem, a concrete one, and you want to compute it and you want to see how to do it, it may be actually also important to see what other information you have about this optimization problem. And the combination of these two approaches, so you're looking at the optimal solution and using these relaxations with symmetry, can then actually be maybe a tailored solution for your actual problem, and can maybe even much further simplify these techniques for you. Okay, there's a lot of literature. Maybe I should give in the last lecture also such a nice literature review. So I just want to mention the first one, which is a paper that is now already 20 years old by Karin Gattermann and Pablo Parillo, which is a very, very nice paper that explains a lot about symmetries and sums of squares. And a lot of the other papers that I mentioned here are inspired by this paper. And a very other nice thing to read is the first article here is, do symmetric problems have symmetric solutions? I mean, this question, if you have an optimization problem, what do you know about the optimal solution? So this is a very nice read by Waterhouse in the monthly. So I really recommend reading this. And with this, I want again to close with a picture, and this time not with polar lights, because I heard that in Pakistan the sun shines. I just wanted to mention to you that also here sometimes the sun shines, and this is how it looks like from above. This is the island of Tromsø. If you look straight ahead, you would see me now, unless, of course, in the picture I was here, so you can't see me because I was behind of the camera, but this is roughly where I live. So it's a beautiful place, and I just want to mention this to you because starting from this year, we have a collaboration with SIMPA. So this is a SIMPA school, so it seems just fitting to mention this. We will have the possibility of 2 selected young researchers to spend, from master to postdoc, to spend 1 month in Tromsø every fall in collaboration with SIMPA. So the details are not 100% clear yet. So there's no official call, but I hope that the call will actually be available in, let's say, the next 4 weeks. If you are interested in this, and this in particular, I want to address to the junior participants. If you're interested, please, you can already contact me now, or wait a little bit until we share this information on Facebook. Then you can apply via SIMPA and maybe spend 1 month, up to 6 weeks, maybe in Tromsø this fall or next fall, and then actually agree with me. You can see polar lights and Carlos's most favorite coffee bar at the university. Thank you so much for the attention.
Thank you very much. Are there any questions from the audience side? Cordian?
Yes.
Yeah. Go ahead.
Yes, I was just wondering if you have like abelian groups and you create these invariant polynomials, it's generated by monomials, right? So that somehow reduce the complexity of the problem.
Yeah, so in general, the question is the complexity of which problem? So you mean calculating these things, or
Yes, calculating the things.
Yes and no. So the problem is, the other problem is that with cyclic groups, you have that the invariant ring is generated no longer as a free polynomial algebra. So you have much more of these invariants. So this may depend on the actual problem that you have in hand. So if you have a polynomial that in the chosen generating set has a very sparse representation, then it might actually help a lot. Yes. So maybe I should say, this is why I stick to the symmetric group, and I said, all the things generalized. So this unicity actually is a very strong helper, because it tells us a priori that, independent which generating set I use, for example, if my polynomial has degree d, then I only need d of the generators to represent it uniquely. This is actually a very strong statement, because this is what is implicitly behind all of these, where I had a short discussion with Carlos, this complexity results when I said, well, whenever n is big, it doesn't change. This is just because this representation is essentially unique. And for cyclic groups, you don't have this unicity. So this means that, going to the invariant ring may actually increase the number of variables or the degrees somehow, if you're in a bad situation. And maybe not necessarily increase, but yeah, it doesn't help so much then.
Thank you.
Cordian, can you go back to the slide where you were discussing about the convexity? And
I can try to. Yes, let me see. So this was a little bit quick at the end, but yeah.
Yeah. So basically, this convexity has under the assumption what you are constructing here, you are only considering the the group here is the symmetric group over the
No,
polynomial
this
ring.
works for all groups. This works for all groups. I mean,
This for all
I
group.
so if you have, I mean, this is very easy. If you have a convex set, you know, if I have a point in a convex set and I
Okay.
take an orbit of the group and then I take the average, then the average will be exactly a midpoint amongst all of these points. So, I mean, taking an average makes the point very symmetric, and because everything is convex, this point will be still in the feasible region, and because my function is convex, we know that also the function value will be not bigger than the outside points. This is just a very simple exercise in convexity.
Okay, and regarding to the partition, can you go to the next slide? Next slide. Yeah, omega. Yeah. So I just I could not understand this particular structure, particularly when go to the next. Yeah. Yeah. The next one. The next one.
Next one.
Yeah.
Okay.
Yeah.
So, okay, what was this? I mean, okay, this again, this was just a huge blow up of notation. I was just saying, suppose I have a point and I know that this point has at most k coordinates and I have a symmetric polynomial. I can always assume that my point is ordered in a way that first I have the first x1 to x omega 1, x1, I have x1, and then I have x. I mean, if I all the coordinates, the first coordinates are the same, the second row of coordinates are the same, and the case rows of coordinates is the same. And I mean, so I just have to know how many ways I can split up n as a partition of k parts. Right?
Okay. So
for every of those partitions, I can assign these coordinates equal and then get exactly such a reduction to k variables.
So this is an unordered partition, right?
This is well, this is an ordered partition, no? Maybe what is an unordered partition? You mean a composition or?
Yeah. So where ordering doesn't. Okay, you can.
Yeah, maybe. So by
yeah.
order doesn't matter. Yeah,
Yeah,
maybe
order doesn't matter. Yeah. So in the later you wrote that if you press next to the slide, yeah, more, one more. You write somewhere, yeah, these many bounded by n plus d power d. Why this is so?
Okay, so this is okay. I mean, if you think about, so I have n slots and I have d things that I can. I mean, so so maybe this should have been a k here. I mean, k partition. I mean, d partition.
Yeah. In terms of, I was trying to understand through k.
Yeah, exactly. So I mean, so if I have a d partition or a k partition, I just mean the number. I have n slots and I distribute d at most d distinct things on these k slots. So then I mean this is at most the number of homogeneous polynomials of degree d in n variables. I mean that's sort of, I mean there's a combinatorics exercise to show that this is something n plus d choose. I mean this is n plus d.
I was just thinking about whether it should not be the Stirling number of n.
Oh, maybe yes. You can. It's related to the Stirling number. Yes, maybe that's. But I mean, I just needed here. So what I wanted to say here is that you can actually upper bound this by something that when you fix d, or k, which is I mean, if you replace d with k, then the quantity that you have here is something that is a polynomial. So if everything is fixed beside n, this is a polynomial in n.
Okay.
And this sort of tells you that you get a reduction. I mean, so here I was saying, you know, you have your n-dimensional problem. You build you build some lower dimensional problems, but you build maybe many of those. So of course, if I would have exponentially many lower dimensional problems to solve, then maybe this wouldn't be a very smart approach. Maybe it would be still better than being stuck with this n-dimensional problem. But actually, here implicitly, what you can show is that a symmetric polynomial optimization problem where the degrees are fixed, is that just the complexity of solving this is just polynomially in n by this very simple reduction.
Okay. Are there any other questions from the audience? Thank you very much, Cordian. Thank you.
But this was a very good question because we will touch on that maybe tomorrow in the tutorial again.
Yeah. Okay. So if there are no questions, let us thank Cordian once again. Thank you very much, Cordian. This was very fast-paced presentation anyways, but we were trying to
Yes.
match your pace. But
Yes,
I
I'm
think
sorry for that. This is why it would have been much nicer being with you, because of course I mean, I always stand here and I talk to myself, and I always understand because I have written those slides.
But
But
anyways,
it's really hard to see a face that is, the
yeah,
reaction of people.
camera ruk sakta hai? Okay. Okay,
No.
and thank you very much, Cordian, and I hope we can meet tomorrow once again for your lecture. And now we let us thank Cordian once again for a wonderful talk. And definitely, these days are really very fast, and I think there are many depths in your lecture, and it requires a lot of time to read and absorb everything. So, but the references and these kind of details and your recording definitely will help us a lot to understand these problems. So anyways, now this is lunchtime here in Pakistan. So participant in Karachi and Lahore, now you can enjoy your lunch. Thank you, Cordian. We'll see you tomorrow once again. Thank you,
Enjoy your
everyone.
lunch.
Bye-bye.